As we reach what is hopefully the tail end of the COVID-19 pandemic, thousands of universities and organizations will need to decide when it is safe to return to normal. Epidemic forecasting tools can help them make that decision. Hi everyone, my name is Balkus, and today I'll be discussing my research into implementing a new COVID-19 forecasting model. As I mentioned, epidemic forecasting helps inform educated public health policy. During the COVID-19 pandemic, the standard model has been the SEIR model, which stands for Susceptible, Exposed, Infectious, and Recovered. The model simulates the number of people in each of these four compartments over a series of time steps. The problem with this model is that it assumes a closed system. It doesn't account for commuters bringing the virus into the region being modeled. And another issue is it doesn't specify how to define the initial values for each of these compartments. As a result, to address these challenges, my research focuses on the multi-level adaptive and dynamic biosensor epidemic model, or m-ADBio. This model models multiple regions in parallel. So the number of infectious individuals in one region can actually impact the number of people becoming infected with the virus in another region if there are commuters between the two regions. This allows us to incorporate commuting data into the model. We also specify different ways in which novel initial value estimation methods, such as biosensor-based aggregation, can be used and how to account for the error that comes from using these methods. Now, a major problem with this is the mathematical formulation is very complex. This is a bunch of gobbledygook that no one really wants to implement while programming. So how can we actually simplify this so it can be used in a practical setting? Well, one valuable mathematical tool is a linear dynamical system. And this is a mathematical model that describes how a system of many variables can change over time. It's really useful, and it's been used for implementing the SEIR model in the past. Now, it's defined by this equation. Xt represents the state of the system at some point in time. And to figure out what the state of the system at the next point in time will look like, we simply multiply by a matrix AT that describes how the system changes. We can do this iteratively over and over again to see how the system changes over a number of time points. That brings us to our research question. How can we actually formulate m-ADBio model as a linear dynamical system? The goal of this is to help us implement m-ADBio as an R package so that it can be used by other people and policymakers can implement their own parameters into the model and run forecasts themselves. So in order to do this, we first need to define all of the parameters of the m-ADBio model as vectors and matrices so they can be input into the linear dynamical system. And there's quite a few of these, so I'll just go through them quickly. We have the population of each region being modeled, the effective reproductive rate of each region, which describes how quickly the virus spreads, the latent and recovery periods, which describe how quickly people become infectious and recover from the virus, commuting matrix, which describes the number of people commuting between each region, and the initial value matrix, which describes the number of people in each compartment at the start of the forecast. To implement this as a linear dynamical system, we simply define AT as a matrix that looks like this, which is similar to the SEIR model, and it describes the change in population between each compartment. And an important variable here is this alpha. We calculate this based on this equation, the mean infection risk, which incorporates the number of infectious individuals in other regions weighted by the number of commuters that might carry the virus into the region that we're considering. And using some linear algebra, we can calculate this by summing this into a vector that represents the alpha for each region. And then we can use this AT matrix to run the linear dynamical system for each region that we're modeling simultaneously. Now, let's take a look at how we actually implemented this in R. Here, we've implemented the m-ADBio model as an R package, which contains 5 functions that can be used to use the m-ADBio model for epidemic forecasting. I'll go through these 5 functions right now. First is the m-ADBio initial values function. This function takes in epidemiological parameters and calculates the number of people in the S, E, I, and R compartments that are needed for the m-ADBio model. And it can also handle different accuracies. So if you expect that the initial values are an overestimation, underestimation for some reason, you can test these scenarios as well. The second function is the next iterate function, which essentially calculates one step of the linear dynamical system. It calculates AT and multiplies it by xt to yield xt plus 1. It's used in this next function. It's a helper function for the m-ADBio function. This is the third function. It essentially is the model itself. It takes in all the epidemiological parameters I mentioned and checks if they're in the correct format, and then runs the model for however many days that you specify. And it basically just runs the simulation over and over using the linear dynamical system model and outputs a data frame of predicted cases for each geography for each day. The m-ADBio plot model plots the output from the m-ADBio function, and it uses ggplot, and it produces a plot like that you can see on the right. Finally, the get cumulative error function calculates the error for a specific point in time. So it calculates the difference between the expected or the predicted cases and the true cases, and divides by the true cases to find the percent error. Now that I've shown you how we actually implemented the m-ADBio model as an R package, I'll discuss the numerical experiments that we used to test whether the model actually worked. To do this, we use a case study of forecasting the number of COVID-19 cases at the University of Massachusetts, Dartmouth for the spring 2021 semester. We explored 3 different scenarios. In the first, we compared the m-ADBio model with commuting data from Massachusetts and Rhode Island, the number of commuters to the university campus, and compared this to the standard SEIR model. In this scenario, we assume that the effective reproductive rate is the same as the state for the university campus. Then, in the second scenario, we actually try to estimate the effective reproductive rate for the university campus instead of assuming that it's the same as the state. And we do this using the EpiNow2 package. Then we compare what the forecast would look like with this new reproductive rate to the forecast that we did previously in scenario 1 for using the m-ADBio model, of course. And then in the third scenario, we actually explore what would happen if we used sensor-based initial values, which might introduce some error into the initial value calculations. These result from over or underestimations, which can arise due to false positives or negatives. And we see how these actually might impact an m-ADBio model forecast. So to run these experiments, these are the parameters that we used. These are actually the same parameters that we've used in our previous studies on m-ADBio model, just updated to reflect the spring semester. So we have the population, reproductive rate, the epidemiological parameters of the virus, and of course the commuters between the states that we selected, Massachusetts and Rhode Island, and the UMass campus. So let's take a look how we did this in R. This R script implements the 3 numerical experiments that we're going to use to test the R package for m-ADBio. But first, of course, we need to install the m-ADBio package, which we can use to do using this command, and you can see that it installs all of the functions that I defined earlier. Then we just basically load in all the data and define all the constant epidemiological parameters for UMass Dartmouth and for the 2 geographies that we selected, Massachusetts and Rhode Island, to simulate in parallel. Of course, we load things like the commuting matrix and the RT values. And these are just, we obtain these from other research, which is linked here. And we also define our own for experiment 2 using this script. I'm not going to run this, but because it takes a long time, but this is basically just the same thing, cleaning data and then running the model with EpiNow to predict what the reproductive rate will be. And so we can run this and then run each experiment. So experiment 1, we see we define the initial values using the initial value function, and then run the model and then get the results. And we can plot this, and the plot will show up on the right. And we can save this plot to the computer and also get relative error for each experiment. So you can see the first experiment, which is the m-ADBio model, we get a very low error of roughly 2%, whereas the SEIR model gives us an error of about 36 or 37%, and that's shown in blue here. Experiment 2 is similar. We define the RT, the reproductive rate, as a list, since that's Anything in a list is run in multiple experiments to compare on the same plot. We can get the error for that as well. And then we can do the same for experiment 3. Now let's examine the results of these R experiments. The plot outputs are shown on the right here with the black circles representing the true cases and the colored bands representing the forecasts of the models. These bands represent the 90% confidence interval. For our first scenario, we see that the m-ADBio model, which is in red and uses commuting data, actually is much more accurate than the standard SDIR model that doesn't use commuting data. This is because the true cases actually lie within the confidence interval, and the mean of the confidence interval actually gets fairly close to the true cases by the end of the forecasting period. Meanwhile, the SDIR model predicts a vast underestimation. For our second scenario, we see that actually estimating the effective reproductive rate for the university specifically using outside tools, the m-ADBio package, is actually very ineffective. So the reason for this is because, one, the red, which is the campus predicted reproductive rate, provides a vast overestimation. So this actually introduces a lot of error into the forecast. And the other reason that this is not adequate is because the confidence interval here is actually very wide. So it's not very useful to forecasters to know that the possible cases are somewhere in this extremely wide confidence interval. So we find that using just assuming that the reproductive rate is the same as Massachusetts for the UMass Dartmouth campus was actually more effective in this case. And finally, our third scenario, we explore the impact of sensor-based initial value estimations. And we see that by the end of the forecast, the forecasts that use sensors to estimate the initial values and possibly overestimate or underestimate, introducing an error up to 10%, which is relatively large, actually doesn't really impact the forecasts that much. It introduces a little bit of error, but it's not incredibly significant, at least towards the end. It's more significant towards the beginning where the confidence intervals aren't as wide. So to summarize these findings, we actually find that the m-ADBio can improve over SDIR by using commuting data, which allows for more accurate forecasts. In addition, our implementation of m-ADBio as an R package allows users to explore different potential errors from the initial values that are estimated in novel ways. And of course, we also noticed that these forecasts were generally more accurate over longer periods of time for all three of the experiments that we looked at. And so this m-ADBio model is probably more suitable towards for long scale forecasts rather than just a few weeks. There are some limitations to this study and things that we would like to improve on. First, we want to find some way to improve the reproductive rate estimation. Because we're forecasting small areas like college campuses, there are a lot fewer cases, which means it's a lot easier for the cases to randomly spike at points in time, meaning there's less predictability. The cases don't follow a gradual curve. So we want to find some way to account for that. And one way that we can do that is by allowing the rate to change during the simulation. So we might implement into the model a way for the reproductive rate to be forecasted, say as an oscillation, or a way for us to measure the impact of potential policy changes on the effective reproductive rate and predict those. Another thing we can do is enable the package itself to be more extensible by allowing users to add more compartments and variables to the model, which would make it more useful for a variety of scenarios. For example, we can allow users to simulate deaths as another compartment, or calculate a model where people can lose their immunity as well. So in conclusion, we found that m-ADBio overcomes the weaknesses of the SDIR model for small area forecasting like universities, which makes it really useful for people who are setting policy for those areas. The R implementation allows these people to model and specify parameters for their own areas that they want to investigate, and they can explore various pandemic response scenarios and test how these impact the predictions into the future. Thank you all for listening. Here are my sources, and I hope you enjoyed the presentation.